All right, question 19.40. Did I write 19.46? Because I meant 19.40. It's just to provide the reagents question. So, I mean, the first thing that we know is that if we have methyl cyclohexane, the only possible reaction we could do, since it's just an alkene, would be to treat it with bromine and light and to do a bromination, which is a radical reaction. So the bromine is going to be introduced at the most substituted carbon like this. Now, before we took our break, I went over the retrosynthesis a little bit and I said, well, if you had this ketone, which could come from the primary alcohol, you could just do a Grignard here to get to the final product. So then the question becomes, how would I install a primary alcohol? Well, in order to install a primary alcohol, I'm going to have to have I'm going to have to make an alkene. Let me show you what I mean. Fun or no rhyme intended. So if I take this and I treat it with an unhindered base, I would end up with the double bond right here. Okay. So if I treat that with sodium methoxide, I end up with the Zaitsev product, and then I could do an anti-Markovnikov addition of water, right? My treatment with borane and THF, followed by hydrogen peroxide and sodium hydroxide. That would give me this compound, and then I'm kind of seeing some light at the end of the tunnel, right? Because now all I have to do is oxidize this with something like PCC or the Swern reagent, and that would give me the desired ketone. And then all I have to do is treat that with the Grignard reagent. In this case, I'm just adding a methyl group, so I'd use methyl magnesium bromide in the first step, and then after the Grignard reagent, you always have to add water in the second step. So there you go. I've done the synthesis of the compounds. It's a total of 1, 2, 3, 4, 5, 6, 7 steps. So we needed 7 steps to do this problem. Let's take a look at D. D, I think, is a pretty tricky problem, and I don't mean like it's a trick question or anything. I just don't think it's an easy question. We're starting with the same reactant. This is methyl cyclohexane, but then we're ending up with something that is a chain. So 1, 2, 3, go. Got a carbonyl here, and then we've got an oxygen over here. So we're starting out with a total of 7 carbons. Then we're ending up with 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're ending up with 9 carbons. That means we've got to add 2 carbons. So I can see that I've got a couple of methyl groups here, right? I have a methyl group here. I have a methyl group here, here, and here. But I also have a methyl group, in the initial compound. So my retrosynthesis, I think about, what if I had just added these 2 methyl groups at the end? Could I do that last? All right, what would that look like in terms of retrosynthesis? If I had if I had, this aldehyde, and this ketone like this, all I'd have to do is treat this with excess methyl magnesium bromide, right? And then that would add in both of these methyl groups, right? It would add in this one and this one. Because now I've only got 1, 2, 3, 4, 5, 6, 7 carbons. So how would I get from here to here? Well, if I could make this compound where I have the double bond right here, and I treat that with ozone, right? Ozone followed by DMS, since it's an alkene, right? I would break the bond there, okay? So let me write it out like this, okay? So if I take the pixel eraser here, and if I erase this, you would end up with this compound, okay? So you've got 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. There you go. And this would be the compound you'd have. So you'd have the right compound. right? So now the question just becomes, how do I get from here to here? And we've already seen that. We saw that in the last problem. First, you treat it with bromine, Br2, and light. Then you treat it with a non-hindered base to make the Zaitsev product. You do an ozonolysis reaction. You bust it open. Then to add those two methyl groups, you would treat it with excess methyl magnesium bromide followed by water. I'm kind of running out of space here, but I wanted to show you something. I have 1, 2, 3, 4, 5, 6, 7. Then if I added another methyl group, I have the methyl group here. I'd form an alcohol here, and then I'd have a tertiary alcohol here, right? Now I need to convert this into a ketone. But if I treat it with oxidation conditions, I'm not going to oxidize this because it's a tertiary alcohol. So that means I can just take it and I can treat it with whatever oxidizing agent I want. Let's choose a SWRM, which is DMSO and oxallyl chloride, followed by treatment with triethylamine. And there you go. So it's a total of 1, 2, 3, 4, 5, 6, 7, 8 steps. Did I miss my nitrogen? There we go. So it's a total of 7 steps to complete that reaction, or to complete that synthesis, I should have said. Oops. So let's go back and find some more space here. And let's try one more. Let's try 19.40, and this is E. So we're starting with this compound. This is called methylene cyclohexane. So this guy, and then we're making an enamine. And we looked at the retrosynthesis of this a little bit last time. Okay, now in terms of my retrosynthesis, right, I told you that since this is our enamine, I would have to have this aldehyde, I have the carbonyl here, and then I also need to have this amine. So I need to have isopropylamine, what's called isopropylamine. We'll look at amine nomenclature later on. So then the question just becomes, how would I get from here to here? Well, hopefully you can see that if you do an anti-Markovnikov addition of water across that double bond, so borane, THF, followed by treatment with hydrogen peroxide and sodium hydroxide, you'd end up with this compound. And then we can oxidize that really quickly. Let's choose PCC to the desired aldehyde. And there you have it, right? Now, if we want to make the imine, what do? We have to treat it with a catalytic amount of acid, the primary amine, and we have to indicate that we're removing water. And that's it. There you go. It's a total of 4 steps to complete that synthesis.